Okay, so today we are finally going to get to correlations. That's promise, hallelujah. Probably not going to do standard errors today. We're probably going to hold off and do that next week. I think it'll flow better next week. But let's first start with some review. So we take a sample from some population to learn about the characteristics of that population. And we might want to get a mean. So the mean, the formula for the mean is going to be the sum of all of the values that we observe over what? Over n, the number of observations that we have. It's one type of an average. So this will give us the balance point for the sample. The formula for the unbiased variance estimate of the population variance is very similar. If we start with the same thing, what changes do we need to make? N minus 1 instead of n.
And to the second power on the x.
We need to put to the second power up here.
And it's x minus.
If we're going to square root it, that would just give us the unbiased estimate of the standard deviation.
Oh, yeah, okay.
And I think I heard the answer from there.
X minus the x.
X minus the mean.
Yeah, there you go.
Right? Beautiful. So this is our estimate of the population mean, which is unbiased. This is our unbiased estimate of the population variance. Groovy? There's a new terminology that I want to introduce here because you may see this in your stats class, and you'll probably see it later on in this class as well. There are lots and lots of ways to calculate variance. And depending on what type of class you're in, you may be given formulas that are much easier to compute the variance by using hand. This is not the easiest formula to use by hand. But I like this formula because conceptually it makes a lot of sense. Because it's the mean of something, or a corrected mean of something. So what is it the mean of? Well, it's the mean of a sum of squares, right? We're taking these deviation scores and we're squaring them. So we have a bunch of squared values and we're summing them up. So we can also represent this as a sum of squares over n minus 1. Sum of squares. Sum of squares, that's all we're doing. We're just taking some values, squaring them, summing them up. Simple. So this is very close to a mean square, right? A corrected mean square. Mean, very similar in form. We're taking the square, we're making a correction, basically same thing. Okay, so the interesting stuff in psychology is not about a single variable. If you have a single variable, you can't really talk about relationships. Think about Harry met Sally with only Harry. It's a boring story. Or with only Sally. Or Harold and Maude with only Harold. Go watch it. So unless you have something else, two variables, you really can't learn about relationships. So, if we're going to have two variables, let's call them x and y, but we can think about any variables that we're interested in. Someone name two variables that might be of interest to psychologists. That wasn't bad enough, Josie.
I just said autism.
Autism. And
Socioeconomic background.
SES. Okay? So we're going to have two variables, autism and socioeconomic backgrounds. And maybe we're not going to have just a yes autistic or no not autistic. Maybe we're going to have some scale that measures autistic types of traits, right? I probably wouldn't be diagnosed with autism, but there's some things about me that might be slightly autistic. Anyway, so we'll have two of these variables. Similarly, SES, it's not like a 1 or 2 type thing. There's a wide range. I have a PhD. That's higher SES. I have, I'm white. Higher SES. What are some things that would decrease my SES?
Disability.
Disability.
Possibly. Possibly.
Possibly.
Glasses.
Say I make $20,000 a year. I don't, but if I did, lower SES, right? So all of these things relate. So SES, for those of you who aren't familiar, it's an indicator of socioeconomic status. So things like education improve socioeconomic status, things like your income improve it, things like the environment in which you live can improve or decrease socioeconomic status accordingly. So we have these two variables, and we want to know if they relate with one another. We have two things, so we can talk about correlations. Correlations, right? A correlation is simply two things, how much they go together. So, before we're going to talk about exactly what a correlation is, there's another concept that we need to think about, and it's covariance. So, this formula, our unbiased estimate of the population variance, we can write this slightly different. I'm going to put two of these, x minus x bar, or x minus the mean of x, times x minus the mean of x. Is that the same thing as this? Yes, it is, right? Because all we're doing is we're taking this thing, whatever that is, plus 2, plus 2. We're just multiplying it by itself. Okay? So, we have this term, we're multiplying it together, so that's just a square in minus 1. We can also imagine this not as the simply the unbiased estimate of the population variance. We can also imagine this as the unbiased estimate of the population covariance between x and itself.
So are those the same thing?
No,
But
not necessarily.
But uses the
In
exact-
this situation, yes.
Okay.
So imagine, we're going to take the covariance of our heights with our heights. So how tall are you? 6'2". He's 6'2". And the mean of this class is not 5'10". Say it's 5'8". Is that still, you said you're 5'7"? Okay, it's not 5'8" then. 5'6"? I don't know, give me one.
I'm 5'9".
You're 5'9"? Oh, right, she's standing on a taller thing. All right, let's say it's 5'6". So, if we think about variance, our variance is basically just a whole bunch of deviations that are squared. We get his one deviation, which would be 8 inches, if he's 6'2", because it goes up to 9, 10, 11, 6 foot, 1, 2. So 8, that's his variation, or his deviation. And then we look at it with himself, right? This is just comparing everyone's deviation, or everyone's variation, with themselves.
So you're comparing how much everyone deviates from the norm, or
With their deviation from the norm, yeah. How much everyone deviates from the norm compared to their deviation from the norm.
so you're comparing the same thing.
That's right. Or not necessarily combining, but or comparing, but combining.
Why do you need to compare with exactly the same thing?
Well, by combining them, we're going to get the variance,
Oh, you combine.
right? So, bad word choice.
Yeah. Okay.
Right? Now let's say we weren't interested in looking at one thing with itself. Instead, we were looking at autism and socioeconomic status. So let's say that autism, we've got scales that range from 0 to 10, and the mean is 5. This will just make things easier. SES, we've got the same type of thing, and the mean is, I'm going to call this y, also equals 5. So then I come to Kat. And Kat, let's say her SES is 7. And her autism is 3. We need to know what this is. So none, all, SES, low autism. Does that make sense? So how could we see how these things vary together? If this is telling us how much something is varying together with itself, how could we figure out how much one thing is varying with something else? The formula is very, very close to this.
Okay, just something that's confusing me.
Yes.
So when it's x minus x, wouldn't that be 0 and you multiply?
Sorry, that should be,
Oh, okay. Now it's good.
yes.
That's-
It's like one of those things, if you're taking a math test and you have a really brutal teacher, 0 points, so 0 points for me thus far. Thank you, teacher. Does that help clarify things? So we're just taking the deviation, your score minus the mean, times your score minus the mean, right? That's how much your score goes together with your score. Imagine my score on elevation. So right now I'm at whatever elevation I am. And think about the elevation for my center mass, which is about right here. So I can go like this, my elevation just decreased. And also my elevation just decreased. It went together perfectly. Jump up, whoa! It went up for a minute. With it going up for a minute. Right? My elevation increased at the same time that it decreased. It went together with itself. It has to, because it's one observation. But not all things necessarily go together. Do autism and SES go together? That's the big question. That's the interesting thing. And the reason I'm presenting in this way is because once you see the connection, it's easy to understand, I think. Hopefully I'll convince you. So, how could we modify this formula? Instead of to reflect how much x goes with x, to reflect how much x goes with y.
Will you change the second one to y minus the mean of y?
Like that? Let's have a vote. How many of you guys think this is a good idea? 1, 2, 3, 4. Is that a hand, Tori? 5. I'm guessing you think it's a good idea because you said it. How many think this is the wrong thing to do? 1, 2, 3, 4. Okay, so we've got 5, 6 versus 4.
Classroom split.
That's good. That's good because that means that there's an opportunity for learning. So which is it? What's the alternative? If that's not the formula, what could we use instead?
Is that the wrong formula?
I'm not saying yet. I want to know what the alternative is.
X minus y times x minus y.
So maybe we could do x minus y. Sorry. Something like that. What? Looks better?
You can't multiply two unknown variables or like two A and B together, right?
You can do what you want.
Okay.
It might not make sense. Let's figure it out. Let's say we have x and y, and the means of x and y, which we do. So we've got, actually, let's just do it with the simple case like this, and see if the math is going to work out. So we have, let's see. So the sum, and we don't even need to take the sum because we're just doing 1 here, which is going to be bad because the denominator will be 0, but forgive that point for just a minute. So x minus mean of x times x minus mean of x versus x minus x times x mean minus the mean of x, right? Because that's the alternative that's just been proposed. So if we do this, we would have 3 minus 5 times 3 minus 5. So that's going to be -2 times -2, which equals 4. And if we do that here, we have 3 minus 3 times 5 minus 5. 0. Now, if we're using y's, we're going to have different values, and it may not turn out to be 0. But if we think about something varying with itself, I mean, think about it. As I jump up and down, is my position varying? Can I describe how that position varies? 0 suggests it's not varying at all. It's always right here. Which it might be. I don't know the truth, but there's enough evidence for me to think that that's not right. So I think that second formula, not so great. Does that make sense? Yes. Are there any other possible formulas that you guys were thinking of besides that one? Because that one was wrong. Sorry.
Maybe if you kept the regular x minus the mean squared, and then maybe add or times it by the y minus. So keep that as x. No, just keep that as x minus x mean, but then add something on the outside.
X minus x?
Yeah.
If it's x minus x, what is this going to be? This whole thing will be 0, and then if we add something on the outside, it'll just be
x minus the mean of x, but then add something on the outside for the y.
Still,
Oh, so like plus y?
Yeah.
The problem with that is if this doesn't really equal this, right? Because then this would have to be plus y as well. So we need this to basically be the equivalent of that when we put the same thing in. So the right formula is actually now. That's it. If you think about it, when you're just looking at x with itself, you just have the same terms repeated. So if instead we want to look at how x goes with y, we're going to have x in one part and y in some other part. In this denominator, it's going to stay the same because you observe my autism and socioeconomic score. You observe his autism and socioeconomic score. For each autism score, you have a socioeconomic score and vice versa. If you have the entire population, you can get rid of the n minus 1, but most of the time we don't, so we will leave that in there. So this is the unbiased estimate of the population covariance. Tells us how much one thing varies with something else. If you think about this original score slightly differently, we have basically deviations. The deviation in x times the deviation in x. Here we have a deviation or a variation in x times a variation in y. Cool? Beautiful. So, that is not the correlation, but that is what the correlation is based on. So, if the covariance, which is also sometimes symbolized S, X, Y, because you have, it's basically like the standard deviation for X times the standard deviation for Y. But I will most likely be using this type of notation to keep it obvious. Otherwise, you see the S really confusing. Okay, so this tells us how much the two things go together. Unlike the covariance of something with itself, or just the variance, which is always going to be positive, this can be negative. Yes, he nods. Yes, why?
Because that would indicate a different type of correlation.
Yeah, it would indicate a different type of correlation. So if we think back to Kat, we had 3 minus 5 was her autism, and times, what was it, 7?
7 and 5.
7 minus 5, so we've got negative 2 times 2, which equals negative 4. Right? So with the variance, we're always going to observe positive scores because we're multiplying something with itself. So if that thing is positive, the answer will be positive. If that thing is negative, the answer will still be positive. However, with covariance, because you're looking at two different things, one could be positive and one could be negative, sometimes you'll observe negative covariance. You can also observe positive covariance if they happen to go in the same direction more often than not. What I mean by more often than not is if we're sampling, we might observe some people who are above the mean in SES and below the mean in autism, even though maybe more of the people are above the mean in SES and above the mean in autism, right? So it really depends on exactly how those things go together. So if the covariance is negative, that tells us in general, not necessarily all the time, in general, as one thing increases, what happens to the other? I forget if I said did I say if it's positive or negative? Okay, good. If the covariance is negative, as one thing increases, the other decreases. What are things that covary in nature that are negative? Or that have negative covariance?
Price of something and the sale of it. Like if that cup costs $1,000, not many people are going to buy it. But if it's like $1.
Supply and demand. And so as the price goes up, demand decreases, right? Classic economics. Also related to psychology because it's the people who are making those decisions. So yeah, economics is just applied psychology. Yeah. I need to tell that to the business school so they can up my salary. Okay. So supply goes up, price goes down. Right? That's another example. Education goes up, number of children goes down. Yeah, the more people are educated, typically the fewer kids that they have. Now this isn't for everybody, right? This isn't something that holds true for me, and you'll hear some people in a classroom when they say that, well, you know, my dad has 2 PhDs and my mom, she's got her master's in fine arts and an MBA and all, you know, all this stuff. And we've got 12 kids. See? Just proved to you this idea is wrong. No, sorry, that's one data point. Each data point that we get is evidence towards supporting or refuting some idea. And we can't look at one data point, we have to look at all of the data combined. Right? Okay, so covariance is how much two things go together. The correlation is going to tell us how much two things go together compared to how much two things could go together. So, what equation should we use? We're going to start with covariance and we're going to do something with it. I'm going to switch the recorder. Okay, so maybe before we answer that question, what would you guys expect the correlation between anything and itself would be? You know?
Just like the same positive.
It would be positive, okay, yes?
Should be a 1.
I thought you were actually answering the way
You
you...
feel like with 1 because it's going to be like 2/2, 4/4.
Perfect. So when he raised his hand, he did it like this. 1. The correlation of something with itself should be 1. Think about a correlation. Where am I? I'm here. Where am I still? I'm here. I'm here with myself and I. So I correlate perfectly with myself. Maybe not over time, but like at least my position. Wherever I am. Woohoo. So it should correlate exactly. It should be 1. So if we take covariance, so the covariance of me with me, what can I do to make this 1? Because I can't, I mean, if you think about it, as I move around, I am varying, right? And I'm varying with myself. So what type of mathematical formula can I do to produce some answer equals what? Put covariance over itself. Like that? Yes, we could do that. That doesn't mean it's right. But we could do that. Now imagine if we had the covariance between autism and SES. What would you expect that covariance would be? Would it be positive, negative, or not? Positive, so as socioeconomic status increases, autism also increases. You might expect that as socioeconomic status increases, there would be less incidence of autism, right? So that's a covariance. What would you predict about a correlation? Do you expect a positive or negative correlation? I'm asking this before I'm talking really about what the correlation coefficient is, because I think some of you have been exposed to this in your intro classes. You have?
A little bit.
What would you expect the correlation would be? Positive, negative, nothing?
I think they probably, well, if it's a positive relationship, they probably would be related.
Well, so it could be related in a positive way or in a negative way.
It wouldn't be one, I don't think.
You don't think the correlation between socioeconomic status and autism would be 1?
No.
1 means what?
Strong correlation.
It means there's a perfect correlation. So for every little bit more in socioeconomic status, we would expect a little bit more autism. And if we had a lot more socioeconomic status, what would we expect in autism? A lot more autism. And if we had a perfect correlation, we would never, ever, ever find people who could say, well, you know, my mom with her 20 PhDs has 12 kids. Because if there's a perfect correlation, that can't happen. So that means the correlation can't always be 1. Now this, even if we did it like this, is always going to equal 1, right? You have negative 53 divided by negative 53 equals 1. That's a problem. Yeah.
But with this, I thought we were using that to measure the correlation between something and itself.
Right. So I asked the question first about something with itself.
Yeah.
Now I want to figure out what the formula for something, the correlation between something and something else is.
Oh.
Right? Because we use that same logic to go from the covariance of something with itself to the covariance of something with something else.
Yeah, okay.
So this can't be right. It's close, but it's not exactly right. Anyone have any other ideas?
Should be the covariance of what you're trying to find for, like this problem right here, over the one for itself.
The covariance, I'm sorry, could you say that again?
So you got this problem
Uh-huh.
over the one for itself.
So you're saying x, like that? That's not going to work. Because that will tell us how much something varies with something else compared to the variance of just one thing. And what we want to know is how much those two things vary together in comparison to how much they could possibly vary together. Any ideas?
Y minus y over x minus x.
Y minus y over...
Do what we did before.
Well, that's going to be 0 and 0.
Yeah.
But maybe we could do something like that, and it will be non-zero.
Take the reciprocal of it, maybe?
This and multiply it by the reciprocal. So the reciprocal of covariance xy is just 1 over covariance xy, and that will give us the same thing. So let's look at this formula a little bit different, Maya.
Okay.
So this is s squared, right? So we can write this differently. So s squared is equal to s times s. We can write this differently. If we're talking about variance of x, this is really the standard deviation of the variance of x is equal to the standard deviation of x times x.
Did you say?
You guys know what a square is, right? 2 squared equals what? 4. How else can we write this? 2 times 2. Right? S squared, Sx squared equals
Oh, that's x.
Sx times Sx. The standard deviation of x times the standard deviation of x. Right? Now, if you think about it, the standard deviation of x, it's not a variance, but it's very similar to the variance. It's just the square root of the variance. And what will it always be? It will always be positive. So the math and statistics, it's not like, oh, plus or minus that thing. We're just sticking with the positive values when we're taking the square roots here. Makes things simpler, although my high school calc teacher would be a little perturbed. So this is just Sx, or standard deviation of x, times standard deviation of x. The answer, my friends, is blowing in the winds. It's Sx times, no,
That's why.
that's y. Confused, that's okay. So think about what these things are. So the standard deviation, it's always positive. And it describes in one way how much variability there is in total in the sample, right? So we have a standard deviation. Here's the total variability for one variable times the total variability for maybe some other variable. In the simple case where we have this, where we've got just the variance, we have the standard deviation, the variability in x, all of it, times the variability in x, all of it. And the most that they could possibly vary is if they went together always in the same way. Does that make sense? Which, for one variable, they always do. But when you have two variables, they aren't necessarily always going to vary in the same way. Does that make sense? Imagine that we have some variable, 1 and 10, and we have another variable, 1 and 2. Let's say they both have the same pattern of variability. This one is going to have more variability than this one, right? Because things are more spread out, that range is bigger. So if this pattern is the same, but it's more spread out, it's going to be more variance. So we can multiply the variance for both of these to get an idea for how much in total they vary. The total theoretical, possible variation. So, if we do this, let's go back to the single situation. We have covariance of x with itself all over the standard deviation of x times the standard deviation of x. And the covariance with itself is just equal to s squared, right? That's what we did up here. So instead of x minus x times y minus y, it's just x minus the mean of x times x minus the mean of x, which turns out to be this. So this is s squared, that's x squared, over sx squared, which equals 1. If, however, we aren't looking at something with itself because clearly that's boring because it always equals 1, we look at the relationship between x and y. We have how much these things go together, how much they vary together, compared to how much they possibly could vary together. So what will this range from? So this is R. This is the correlation coefficient. Zero to 1. So if these things don't go together at all, or these things don't go together at all, then actually this, that would be that. That would be infinity. But if they don't covary together at all, then this should be 0 over whatever that is. That will equal 0. If they vary perfectly together, what things vary perfectly together? What two different things? My height in centimeters and my height in inches. They go together exactly. I am 6'2" tall. I am 193 centimeters tall. That should be pretty close. If I was another inch taller, I think I'd be like 2-point-some centimeters taller. For each additional inch, I know exactly how many additional centimeters I should be. Or for each fraction of an inch I get taller, I know exactly how many more centimeters I should be. Does that make sense? So, for something like that, X and Y, they will both vary in the same way, some amount. And because they are varying in a way that is perfect, they are varying as much together as possible. There's no deviation. Think about like new couples who just like stick together like glue, right? They're always around holding hands. Right? For that period of time, their positions are perfectly correlated. I'm a little bit to the side, but other than that, it's there, right? So, if they are both covariant together as much as they possibly could, then this should not equal 0. Instead, this will equal 1. So we could have R is equal to 0, which means no correlation. This doesn't mean that they don't go together ever. What does it mean?
They just didn't go together when you observe them.
Not necessarily. They could have went together when I observed them.
Well, and then not,
More often than not, they don't go together. I'm gonna say no, but you're close.
They just cancel out?
The variations cancel one another out. So sometimes they're going together, sometimes they happen to be together, and sometimes they don't happen to be together. There's one other piece that I want to add to Cassie's definition. More than you would expect due to chance. Yeah, you got that?
They don't go together more.
More than you would expect by chance. This semester, I have a relationship with you. You're my student. We're in this room at the same time. Last semester, you were not my student. Did we ever bump into one another? I have no idea. It's possible that you were in the library one time that I was in the library. You would expect us to both go to the library occasionally on a college campus, right? So just by chance, we might both be in the library sometime together. If there's a relationship, you would expect us to be in the library, in the classroom, or in other places more often than you would expect just due to chance. Does that make sense? So it doesn't mean that you never observe them together. What it means is that you don't observe them together more often than you would expect due to chance. Because sometimes someone might have a high SES and be high on some autism scale. Even if there really was no correlation, just due to chance, right? So, no correlation. We have R could equal 1, which means there's a perfect positive correlation. So this is a perfect positive. And I really like positive. I really like how she said perfect positive, because she didn't just say it's a perfect correlation and leave it at that. Which means that the word positive is important. So if there's a perfect positive correlation, what could there also be? Perfect negative correlation, in which R would equal what? Negative 1. Right? So, we have R equals 0, no correlation. R equals 1, that's a perfect positive. R equals negative 1, that's a perfect negative. So, R is less than or equal to 1 and greater than or equal to negative 1. Right? And you can imagine when something is going with itself, that's 1. For every dollar I spend, what does that negatively correlate with perfectly?
Dollars in your wallet.
The dollars in my wallet. For each dollar I spend, I have one less dollar to spend. Does that make sense? That would be a perfect negative correlation. So most of the time in psychology, we don't have perfect positive or perfect negative correlations because we're usually not interested in the correlation between degrees in Fahrenheit and degrees in Celsius. We're interested in things where there's a lot more variability. Level of SES, level of autism. Amount of amygdalar activity. Amount of violent tendencies. Right? So those things aren't going to vary perfectly. Okay, so when we talk about correlations, we can talk about two things. We can talk about the direction of a correlation. We can also talk about the strength of a correlation. So, if R is less, I'm just going to write it. No time. So if R is like that, what part of R tells us the direction of a correlation? Positive or negative. So the sign, I could write this like that, right? So it's the signs that tell us the direction. So as I indicated, as ice cream sales increase, drownings increase. Positive. The direction, they're both moving together. As education goes up, number of kids go down. On average, more than you would expect due to chance, right? As one is moving up, the other is going down. More kids, less education. More education, less kids. They're moving in opposite directions. So what tells us the strength? Absolute value. So, strength is indicated by the absolute value of R. So those are the absolute value signs. So to make sure everyone's on the same page, negative 0.7. What is the absolute value of negative 0.7? 0.7. Is everyone on that page? So this means that if we have a correlation of negative 0.7 and another correlation of positive 0.7, which one is stronger? They are the same. Now they're not the same correlations, but they're the same in strength. They're both equally strong correlations. So, the farther away R gets from 0, the stronger that correlation is. In which way it's moving away from 0, that tells us the direction of the relationship. Whether the two things are moving in the same direction more often than we would expect due to chance, or moving in different directions more often than we do to chance. It's like when Dorothy is asking the scarecrow, which way? What type of correlation is that between the directions he's pointing?
Negative.
It's negative. Yeah. Groovy? So, if you look at a scatter plot, what type of correlation would that be? Positive, right? If we draw a line of best fit through that data, it's a positive correlation. Now, if I ask you how strong that is, that's hard to just compute on your own. But let's say we're comparing this to this. Which is stronger? Second one, right? Because the second one, the dots are more tightly compacted around the line. So when we're talking about correlations, it's very similar to the ideas of regular variations. Except instead of looking at variations between each point and the mean, we're looking at the variations between each point and that line of best fit. So something like this is more strongly correlated than something like this. And as we go crazy, there's no correlation, which means that that line is just as good as that line, which is just as good as that line, or any other line that you can make. So, scatter plots are great for visualizing correlations. Just see, can I put a line through that? It makes sense, it fits the data pretty well. If you can, you probably have a correlation. The direction, the slope of that line will tell you whether that's positive or negative. And how tightly compact those dots are around the line will tell you the strength. Cheers.